Every time you plug something into a wall in Great Britain, you're tapping into a massive, synchronized machine that beats exactly 50 times a second. That 50 Hz frequency is the vital sign of the entire national power grid. If that pulse slows down and hits 48.8 Hz, the system triggers a defense mechanism called low-frequency demand disconnection. It automatically cuts power to entire neighborhoods to keep the wider grid from totally collapsing. For decades, engineers relied on a physical failsafe to ensure the grid never reached that critical threshold. They called it inertia. To understand inertia, you have to look inside a traditional coal, gas, or nuclear plant. At their core are massive metal turbines, weighing thousands of tons, spinning in perfect lockstep with that 50 Hz pulse. All of that rotating metal stores an enormous amount of kinetic energy. If a plant trips offline, the sheer momentum of those other spinning turbines acts as a physical shock absorber, naturally resisting the drop in frequency. For most of history, grid stability was guaranteed by sheer, unbreakable physical mass. But the mechanics of power generation are changing. Today, a growing share of electricity comes from wind, solar, and underwater interconnectors, technologies known as inverter-based resources. These modern sources inject power into the grid electronically. They lack physical mass spinning in sync with the grid, which means they provide zero physical inertia. Across the grid, static solar panels and wind farms are steadily replacing traditional power plants at a massive scale. Stripping away those physical shock absorbers makes the entire system lighter. Without that spinning momentum, a single disruption causes the frequency to drop much faster and more steeply than it would have a decade ago. The transition to clean energy changes the mechanical nature of the grid, trading physical resilience for a system that reacts instantly to any disruption. This creates a major operational challenge. Recently, the National Energy System Operator, or NESO, laid out a new strategy for this lighter grid in its Frequency Risk and Control Report. In that report, they proposed intentionally reducing the grid's minimum required inertia. They want to drop the floor from 120 gigavolt ampere seconds down to 102. Reducing the inertia floor would save £96 million a year, because operators would no longer have to pay fossil fuel plants to stay turned on just for their spinning mass. This chart shows how grid operators calculate the trade-off, using an ICER risk curve. This line divides acceptable risk in the green zone from the unacceptable threats in yellow and red. Pushing toward the green edge is an intentional gamble based on probability. In the modern era, grid stability is a high-stakes economic balancing act. Operating with less inertia is possible because we have a new tool to catch falling frequency. It's a service called dynamic containment. Practically, dynamic containment relies on vast arrays of white containerized battery units. These batteries are monitored by smart software. Detecting a drop in frequency, they actively inject stored power into the grid in fractions of a second. This is a digital reflex. Instead of the passive momentum of old metal rotors, the grid now uses computer-controlled speed. We have traded the blunt instrument of physical mass for the precision of ultra-fast digital response. Swapping physics for software introduces complex new blind spots. An independent review by energy researcher Keith Bell warns a low-inertia grid carries unpredictable risks. One concern is loss of mains protection. A localized fault causing a voltage drop might make solar farms misinterpret data and disconnect. This creates a cascading failure. If enough sources drop off, frequency plummets faster than batteries can react. Safety relies on software controllers and precise data measurements, rather than the unbreakable laws of physics. A digital safety net requires near-perfect computer simulation, because if the algorithms fail to predict a disturbance, there is no physical momentum left to save the grid. The definition of a secure grid now rests on algorithmic predictions and battery deployments instead of giant spinning metal rotors. To handle this change, the 2025 review calls for updating emergency protocols to ensure they match the behavior of a lighter, faster system. It also means enforcing stricter ride-through compliance, requiring renewable energy providers to widen minor disturbances without instantly disconnecting. The projected savings prove that we can integrate vast amounts of renewable energy as long as we respect the limits found in the modeling data. System frequency serves as the ultimate speed limit of the green energy transition, a balancing act that will determine how we reliably power the future.